So, welcome to this Sunday's installment, your favorite installment of the mock technical interviews. We've got three sessions today. We're starting the first one right now. It'll be a mock leetcode with our friend and candidate Aneesh from the community. Let's get started right into it then. Do you want to just give a quick introduction?
Yeah, sure. Hey everyone, my name's Aneesh. I'm a new grad from UBC, and I'm currently preparing for technical rounds with Tesla and an investment firm in Vancouver. So,
That's great.
hi.
Okay. Thank you for the introduction. Let's get right into it then. So, you're free to take. Oh, by the way, what's your preferred language?
Python is fine.
Python's fine. Okay, great. So feel free to take notes as I dictate the problem, and if you have
Yep.
any questions, let me know, and we will go back and revisit it. So
Okay,
today's
sure.
problem we're going to be talking about is going to be the k closest points to origin. So in this problem, I would like you to implement a function called k closest. Okay, it's going to accept an input of a list of points and a number k, an integer k, and I want you to return the the points from the list of points that are closest to the origin.
Closest to the origin. Cool. And when we say origin here, of course, we're referring to like on a Cartesian plane, the point 0, 0.
Mm-hmm. Yep, that's right.
Right. Okay. So, just to clarify a bit about uh, the inputs that we have here. So when we say list of points, everything is two-dimensional. So we have something like a list, 1, 2, 3, 4, 5, 6, whatever. And this would be our input, and then our k would be any integer that's within the length, right? Like we're not going to have a k that's larger than the length of this array.
You can assume that the inputs are good faith inputs. Yeah.
Great. Okay. So let's say that can k be 0? When you say good faith, I'm
K
what?
can be zero. Zero is a valid input. Yeah.
Great. Okay. So 0 less than or equal to k less than or equal to the length of points. So we'll call that the points there, and our negative points also allowed. So like negative one, for example, something on the
Yeah.
other side of the
Yeah, for
grid.
sure.
Great.
Yeah.
Okay, cool. So first, I just wanted to run through some test cases with you, just so we have a good picture of what we want the function to do before we kind of jump into anything else.
Mm-hmm.
So okay, let's just take the first test case I have, for example, 1, 2, 3, 4, 5, 6. Um, and oh, I should clarify this. When we say closest, we mean like the Pythagorean distance to the point, so like x squared plus y squared.
Yeah, Pythagorean distance, Euclidean distance.
Okay,
Yeah.
great. Okay, cool. Obviously, when I say that, I really mean like x minus x1 squared plus y minus y1 squared. But in this case, x1 and y1 are 0. So I'm just gonna, for simplicity's sake, it's just easier to just say x squared plus y squared.
Sure. Yep.
Um, yeah, just easier to think of it that way. So let's go through the test case we have here. So say we have this array 1, 2, 3, 4, 5, 6. I copied the empty space, sorry. And let's say we have k equals, I don't know, k equals 2, for example.
Mm-hmm.
Then we would expect to return 1, 2, and 3, 4, correct?
Yep.
Inside an array.
That's right. Yeah.
Okay, cool. So I just want to think about any potential edge cases that we'd want to go over before we get into this. If we have, are we allowed duplicate points? And if so,
Yeah. You
should we
can.
return both or just or arbitrarily break ties?
Yeah. Duplicate points are allowed, and I mean, points don't have identity in the sense, so it doesn't matter which of the two identical points return. They're the same point in that sense.
Okay, great. So if we had the input 1, 1, and then 1, 1, and then k equals 1, then we would just expect the output to be that.
Yeah. That's fine.
Cool.
That
Okay.
sounds reasonable.
Sounds good. So let me just write out a function signature, just so we can have that there. Or I guess we could set that class. And then we can talk a little bit more about this. Uh, so just writing out the function signature, points is a list, plus int, and k is an int. Uh, says my syntax is undefined here. Sorry, I'm not sure which one I'm supposed to be like importing.
I think it's from Python import list.
Okay, great. Yeah. Usually leetcode handles it, so I'm not always sure. But thank you. Okay. So
What's the return type on this function?
it's a list of int. Sorry. Thank you.
Okay.
Okay. So let's just have that here for now. We don't need to worry about the actual thing here. So my first like naive idea here is to kind of iterate through each of these points and compute their Pythagorean. I think computing the Pythagorean distance needs to be done regardless.
Okay.
Um, at least now I can't think of any way around that. But my kind of naive idea is to create a um, like a hash map kind of that would associate each point with its Pythagorean distance, and then sort that, and then just return the first k of those. Um, but I
Sorry,
think
just
there.
to hash. What is the key and value of the map you're proposing?
So the key would be the point, and then the value would be the distance. But A, that's not going to be as efficient as what I think would work better, which I'll get to. And B, that would create issues with potential duplicate points, which we don't want to have to have to deal with. So my next idea is to use especially when I see something like k closest, my like instinct is to use heap. So in this case, it would be it's k closest. So k closest implies smallest distances. So this would technically be a let me think a min heap, and we would pop off the first k. Or what would be easier is to maintain heap of size k and return this heap after iterating through the list of points and computing their um, distance from origin. So is that clear, or is there anything I can like kind of clarify with what I mean by this?
No, that proposal is clear to me. I just want to make sure that is there a map still in in this picture here?
Um, so I need to think. I think there. I'm just gonna take a second to kind of sketch it out in my
Yeah,
head
think about that.
before
Yeah.
I give an answer to that. Um, so the only thing, so there could be a map associated with it. The only thing I'm kind of trying to reconcile right now is how to deal with duplicate points, because um, if we have, for example, in the example I showed up here, 1, 1, 1, 1, and then say 2, 3, and then k was equal to 2, we'd obviously want to pop both of these points and return them in the end. So I'm just trying to think about how we can ensure that that would be done if we used any sort of map to actually um, create our max heap. Because
Okay.
in the max heap,
Yeah.
obviously, the distances or the value that we're kind of I say quote unquote sorting by would be the actual distance from the origin, which would be obviously duplicated if we have either duplicate points or points with the same um,
Is that an issue?
distance. I don't think so. I'm just trying to think about how I'd code it up
Mm-hmm.
because I'm just trying to think about how I want to initialize all of that. But no, I don't think that would be an issue.
Okay. Then we can proceed with that.
Okay. So let's just go import heap queue because I think we definitely will need a heap. So first and foremost, we want to compute all of the. Let's just turn that for now, so Python doesn't complain. So first things first, we do want to compute each of the distances here, and we'd want to associate each point with its Pythagorean distance. So how would we want to do this? So what we could do is with each So one thing that we're gonna have to obviously work around is in Python there are no max heaps, only min heaps, but we can always just multiply by -1, for example, if we wanted to use that, which I'm thinking might work better. So again, just give me a second to think about how I want to initialize this, and then I'll continue writing. And if there's anything, again, unclear about what I've said, let me know. I know I've kind of said a lot of different thoughts right now, so.
Yep. No, I'm still with you.
Cool. So, a few different points. Let's say. And for simplicity, I think I'm just going to stick with the actual squares of the distances here. It doesn't matter because these are all positive integers, so it's not going to matter whether we take their square roots or not. So just to save us a bit of extra computation, I'm just going to compute the square distances. And
can you elaborate a bit on that one?
Sure. So if I had like 1, 1, for example, again, like from up here, I'm just going to associate 1, 1 with obviously the distance from the origin is going to be the square root of 1 squared plus 1 squared, which is equal to square root 2. But since the square root function is monotonic, we can just leave it as 2 and just associate each of these with the squares of their distances.
Okay, yeah, that makes sense to me.
Okay, cool. Yeah, again, just for ease of computation, ease of readability, I think that just makes more sense
Yep.
to leave it that way. So like I mentioned, we want to maintain a heap of size k, and we want to, if we find a value that is, okay, yeah, I think I have an idea of the algorithm here. So we are, like I said, maintaining a heap of size k, and what I'm going to do actually is make this a max heap. So the reason I choose to say a max heap is at each like computation of our at each computation of the distance of the point as we iterate through this array points, what my idea is we're going to check the top element of the heap, which of course is going to be the farthest away, because we're going in like increasing order of distance. And if the current value that we're currently looking at is smaller in distance, then we're going to replace it in the heap of size k. And that'll ensure that all the values on there are the k closest.
And I want to just be one more thing. I don't know if you mentioned this explicitly, but is the heap here a min or max heap?
So the heap, since it's Python, it is a min heap, but we can just convert it into a max heap by multiplying each distance by -1 and then pushing them on.
Okay, yeah, that sounds good to me.
Okay, cool. Yeah, which is annoying, but whatever. That's not a big deal. We can deal with that. So again, I'm just thinking how we want to. Oh, okay. Actually, I think I do know how we want to do this. So we're just going to create a tuple each time that associates the distance of that point with the point, and then compare it with the top element of the heap, and then push it on if it is a closer distance than whatever the top element of the heap is.
Okay.
Okay, cool. So let's get into some code. Is there anything else about that algorithm or any of my test cases I can clarify?
I think it's pretty clear so far, but I want to see some more implementation detail. So let's move on to the implementation here.
Okay, great. So let's say, I don't know, heap equals that. We'll just initialize an empty array for now. So now for point in points, let's say that x equals 0.0, y equals 0.1, and we'll say that the distance is equal to x squared, or x squared plus y squared times -1. Again, because we want to convert this into a max heap, so this will be a bit more straightforward. Okay, so let me think about the next step here. So the next step is if the heap is not of size k, then there's no issue, and we can just push on this current point. So let's say tuple equals, no, we can't do that. I don't know. Pair equals distance, and then point. So my understanding of if I try to make a heap out of this pair is that the like Python implementation is going to sort by the distance, so the first value. Um,
Mm-hmm.
Feel free to correct me if that's incorrect, but that's the assumption I'm going to be sticking with here.
Yeah, that's correct.
Okay, great. So if and heap, let's see, if it's less than k, then there's no problem. We just want to do heap q dot heap push there. Let me think. Is there any other issue with that? Oh, right.
You need the heap.
Yep. Heap pair. Okay. Let's think. Are there any other steps that we need to take at this point? We push the thing on, and of course we're going to return we know that at the end we're going to return the heap, so we can just that there. Okay, so otherwise, if the heap is of size k, then what we're going to want to do is, let's think, let's say farthest equals heap 0, so the top of the list. Now, if distance less than farthest 0, we're going to do heap q dot heap pop, and right. And otherwise, heap q dot, and then heap q dot heap push, heap paired. Yeah, okay. I think I'm pretty happy with that actually. Let me just kind of run through this algorithm in my head here. So okay, let's just say we have let's just start with a simple example. I'm sure you'll have like your follow-ups and stuff, so before I get into those, I just want to clarify with a test case that this actually works the way I intended to.
Mm-hmm.
Oh, can I run anything here, or do I have to do this like in my head?
You can run it. I mean, I don't care if you run it or not, but you're allowed to run it. Yeah.
Oh, okay. Uh, it's fine. Let's just stick with this. I feel like it's better practice for interviews because I might not be able to run anything. Okay. So if we have 1, 1, 1, 2, so on the first iteration, the heap, so this is the heap is going to get -2 and 1, 1. Cool. And let's say k is equal to 1.
Mm-hmm.
Then on the second iteration, heap is going to get, oh, I did make a mistake. Yeah. I'm returning the heap here, but we just want to return the points in the heap. So let's just, since it's not going to, I don't think it's going to affect the time complexity, which I'm sure we'll get into. Let's just quickly do that. So for heap. Oh, I should clarify this now. I should have done this earlier. Is there any restriction on the order that we return these points in?
No, yeah, there's no restriction.
Okay, great. So then we can just do res dot append pair 1. Okay, cool. So yeah, so the heap is going to be -2, 1, 1, and then 1 plus 4 is 5, and then that's obviously going to be distance is, right, and this should be distance greater because we're dealing with negative values here. Yeah, this should be distance greater. So if the distance is greater, we're going to pop that on, and then we should be good to go, because of course -5 is going to be the next one, and that's 1, 2. -5 is not greater than -2, so we're not going to pop anything, and we're just going to continue. Okay, I'm pretty happy with that. I feel like I'm satisfied with what's there. Do you have anything you want clarified or anything I could explain better?
Nope, I'm pretty happy with this as well. Let's move on to the time and space complexities for this function.
Okay, yeah, cool. So so the bottleneck is obviously going to be in this for loop here in terms of time complexity. So let's just get this out of the way. Over here, this is just going to be in worst case linear time with respect to the number of points that were inputted.
So n is equal to the number of points.
Yeah, and it's
Okay.
the number of points. So
Okay.
this for loop here is not going to be the bottleneck. So let's just get that out of the way. This is going to be O of n with respect to, again, number of points. Now over here, if I remember my heap operations correctly, I believe the time complexity of heap push and heap pop are log um, of size of the heap. The reason that this approach is like optimal compared to some other potential brute force ones is that here the size of the heap is actually k, and since k is less than or equal to n, um, in the average cases, this is actually going to create, this is going to be optimized. Of course, there's the possibility in which k is equal to n, but then we just end up with n log n, which is still faster than or as quick as we could have wanted it. And then since we're iterating over all the points here, this is going to be an um, O of n for loop with of course all of these are constant time operations. So these log k operations down here, let's just log k, and then of course if this had, and this is also going to be log k. So
Mm-hmm.
in total, this algorithm is going to run an O of n log k time. O of n times log k time. Yeah.
That makes sense to
Okay.
me. I did want to just check on one thing here. This is
Yeah.
do I want to double check the space of this loop, or the time of this loop?
Yes. Thank you for that. That would be O of k. My bad.
Okay.
So in total, yeah, because the heap is size k, right? We
Mm-hmm.
maintain that. So in total, this is heap. This is O of n log k plus k time, but of course, asymptotically, that's just going to reduce to O of n times log k.
Yeah, that makes sense. Let's go to the space.
Yeah. Let's get the quick stuff out of the way. Of course, these are constant variables. X is, constant, y is constant, distance is constant, and each individual one of these pairs is constant, but we're going to have, in the worst case, the heap is going to be O of k space, and that is also true of the result array. So I'm going to say that the space complexity here is O of k, so linear with respect to k.
Mm-hmm. Okay. And so we're applying that the only two pieces of memory allocating are the heap and the result array, essentially.
Um, Yeah, let me think. Is there anything else that's not constant? So each of these distance, so this distance when we create inside the for loop is
Mm-hmm.
constant. This is constant. Yeah, so I think those are the only things that scale with the algorithm.
Is adding to the heap require extra space?
Um, for this equals create extra space. Well, let me think. I can't think of why it would because we're just going to
Mm-hmm.
be popping and then pushing an element on, so the heap is going to remain the same
Mm-hmm.
size.
Yeah.
So I don't think so.
Yep, that makes sense to me as well. Okay. Let's move on to a quick follow up on this one.
Mhm.
So in this follow up, we're gonna expand the scope of this question a bit. Okay. So we're gonna keep the core algorithm the same, but we're gonna add on a different way to use this. Okay. So now, instead of an algorithm or a function called k-closest, we're gonna have two functions. Okay. So one function is called addPoint. Okay. addPoint adds a point to whatever structure you want to choose to store the points in. It can be a heap. You can choose to switch to something else. Okay. And then there's going to be okay, and then you'll have the new k closest. So to keep it separate, let's call it m closest. Okay, m closest. Okay, and so m closest takes a integer m.
Yep.
Okay, and returns m points in the structure that are closest to the origin.
Okay. Okay. Uh, sure. So, okay, let me think about how we want. So just these two, m closest and add point.
Mm-hmm. For now.
Okay, so let's just to confirm like what the function signatures look like, is add point going to be something like takes a list int, so that's just going to be a list int. It's going to consume a list int, which is just going to be a pair xy, and it's going to return none. Is that correct?
Yep, that's fine.
Okay, and then m closest, is that going to take an int and then return list of points?
Yep. List of points essentially. So list of ints.
Yeah. Okay. So also, are we coding this or just discussing this?
We can discuss it first, and then depending on how confident I am, we can either move to the next follow up or we can code it up.
Okay. So the challenge here, of course, is that since so we're sticking with k closest, but then also adding these two functions. Is that correct, or is that like these
Uh,
are kind of replacing k closest?
they're kind of replace. I mean, you can use k closest as a helper if you want, but you can
Uh-huh.
imagine that this is a different universe, and in this universe, you might want to call k closest, but you do not have to depend on k closest at all. So that you can think of this as a new problem.
Okay, sure. So so we want to add a point to some structure and then also return the m closest. So my first kind of thought is the simplest way I could see this working would be something like we keep k closest as it is. And then um we add a point to just an array. So like add point just adds point to list, and then m closest would just call k closest with whatever our points array is so far, with uh, m as the integer. Now, with repeated calls, this is not going to be the most effective way to do this, which is why I'm hesitant. But I don't think there's anything incorrect with approaching it that way to start. What do you think?
Can you repeat the part about? Can you repeat the part about the significance of m here? So how?
Yeah, so then
Yeah.
when we call m closest,
Mm-hmm.
what that would entail would just be we call k closest, but then the arguments are the points so
Mm-hmm.
far, like
Yeah.
in the array, and
Mm-hmm.
then m.
Okay. Let's talk about sure. So let's just think about this. That's fine to start. What's going to be the time complexity of add point in that case?
Add point would be constant because we're just going to add it to an array. We're just going to append it to the end.
Okay. And what would be the complexity of? So let's just quickly write this down, right? So this is the first approach. So the times complexity for add point, and then m closest. So for this one, right, the time is going to be 01, right?
Mhm.
And then what's the space of this going to be for add point?
This is gonna well the function itself isn't going to take extra space, but then the array is obviously growing with
Mm-hmm.
the number of calls to add point. So I'm not sure how I would formalize that
That's
though.
fine. We can then just discuss that the class overall. Class overall will have a space complexity of, and you said what is this? What is the space complexity here?
It would be n, where n is the number of points that we add.
Okay. And what would be the time complexity of m closest in this case?
So if m closest just consists of a call to k closest, then it would be the same as before. So it'd be n log k or n log m. And no, sorry, go ahead.
No. Yeah. Okay.
And then the space would again be O of m.
Yeah, that's right. So this would be. Okay. Let's think about any ways to improve this, right? So, for
Mhm.
example, so I'll put it this way. For example, in this case, um, adding points is very cheap,
Yep.
and determining m closest is very expensive,
Yes.
right? And so this might be ideal if, for example, we know that the users typically call add point a lot and they call m closest infrequently. Okay,
Yeah.
let's think about the opposite case. Okay,
Uh-huh.
so what if in the opposite universe, users don't add that many points, but they still add points, right? They still add some points, but they call m closest very very frequently. Okay, in that case, what are some strategies we can use to kind of shift the balance a bit?
Right. So yeah, so that's what I was worried about when I first proposed this. So the first thing that comes to mind would be, of course, inside add point is a more like sophisticated data structure than an array. I'm thinking potentially a heap inside add point could potentially work. So each time we add the point, the heap is just consistently growing, and then inside m closest, we pop m times, for example, which in terms of complexity would be um, m times now log n. So
Do you want to write that down? So let's say,
yeah,
yeah. So go ahead.
yeah. Sorry. So in this case, add point, we add to a growing, because of course add point in this case is not going to have any knowledge about what m is, right? That's just
Mm-hmm.
an argument inside m closest.
Mm-hmm. Yep.
Right. So if that's the case, then we don't have the luxury of um getting rid of any points in add point. We do have to some way or another maintain all of them. Like we need to have some sort of record of all of them, because we don't know how many we're going to need to pop off later. So add point, we add to a growing heap. Let's say a max heap. No, actually in this case, yeah, a max heap is fine. Because we can no, this will need to be a min heap. Sorry,
Mm-hmm.
min heap. Because the approach to in k closest is not going to be. We can't identically use that for this. Uh, m closest, we pop m elements off of this heap. So let's just quickly go into time. So the time of this, each element is going to be, since there's just going to be a straight push, we're not going to have to worry about anything else. It's just going to be O of log n.
Mm-hmm.
And
Good.
then space will be O of n, where n here is just the number of calls to add point.
Yep.
And then in m closest, this is going to be time, or let's just fill this out here for completion's sake, just so we have a record of that. So then the time here, if we pop m elements off, so that's going to be m calls to heap pop, and then this is a heap of size n, so this is going to be m of m times log n. I can't even tell where my brackets end now. But no, it
I don't
matters.
care about the brackets. Don't worry about that.
Yeah, yeah, I know. It's just weird. That's and then space. There's going to be a result here, so the space of that is going to be O of m. So, but other than that, we're not going to create any
Mm-hmm.
extra, or we're not going to have anything other than potentially constant operations in there.
Yeah, that sounds good. But I wanted to focus a bit on so this is good. I like where we're going. As a next idea, I wanted to focus on this time complexity for m closest, right? So this is
Hmm.
m log n, where m
Hmm.
is the input, how that's m closest,
Hmm.
and log n is the size of the heap,
Hmm.
essentially, right?
Yeah.
Um, why are we using a heap? Can you justify that?
Um, I think it's the most like it's the most intuitive idea, at least now, without a significant amount of refinement. I'm thinking
Mm-hmm.
about using a heap because it'll make it easiest for the first point in whatever data structure we use to be guaranteed to be the closest, and then as we pop, we can still guarantee that the top element is the closest to the origin.
Uh, yes. Is a heap the only data structure that can do that?
Um, no, I'm trying to think of what else we'd want to use though. Uh,
Maybe you can back up another one as a. I just make sure that's on the same page. Why did we use a heap for the original problem?
so we used a heap for the original problem because of its because we can if we're maintaining a heap of size k, then we know the top element is going to be whatever's furthest from the origin.
Mm-hmm.
So that's a constant comparison with the next point that we choose. And then putting it onto the heap is going to be uh, log k time, which is faster than, for example, having to sort an array over and over, or I'm thinking what else we could potentially we want to use. Having to check inside like a hash map or something like that over and over. This would make it so that we can just take the first element, guarantee that it's the farthest, and then do a comparison with whatever we're currently looking at.
Mm-hmm. That's right. And that is only relevant because k is less than n.
Yeah, in most cases.
In almost every case. Like there's no guarantee, right? So you can't assume that k equals n, right? So k is less than in most cases, and so
Yeah.
therefore, yeah, your justification makes sense. Um, okay, why don't you continue your train of thought on other options that we can use for time optimization?
Sure. So let me think. So so of course, what you're getting at here is we don't use a heap at all in add point, right?
Not necessarily. I
Like,
mean, either we don't use a heap and we improve the time complexity. I'm not saying add point or I'm close. I'm saying either we don't use a heap and we can
hmm
potentially improve the time complexity, or
hmm
you prove to me that a heap is the optimal time complexity.
Okay. All right. Makes sense. Okay, then I'll need to think a bit more. So in terms of other potential data structures that we can use,
Mm-hmm.
I'm thinking about what else could potentially make sense. So and in this case, are we trying to like think about optimizing for multiple calls over and over, or are we just thinking about like a single call and just worrying about that like for now?
So the original follow up was that um, we this user is now calling m closest very frequently, and
Right,
add
right, right.
point not that frequently,
hmm
right? So the goal is minimize the time complexity of m closest. Essentially, minimize the time complexity of m closest at all cost. That is
Even
your
at
goal.
cost to add point. Okay.
Even at cost, anything. Yes, add point included. That's correct.
Okay. Um, in that case,
By the way, that's not a hint saying that add points time complexity must increase. I'm just saying at all costs, and you can use more time in add point, or you can use more space in either function. That's what I'm saying. If you need.
yeah,
Yeah.
okay. Yeah, that makes sense. So, okay, yeah. So now I think the next something even simpler than a heap that we could use if we're like thinking, okay, we want to just optimize for m closest is in add point. Uh, we just add points to a list and sort each time. Now, if we do this, of course, add points time complexity um, is going to balloon. It's going to be a lot bigger than O of log n.
Mm-hmm.
But now the trade-off is that in m closest, each time we're just going to pop off. We can just iterate through this array once, add the points, add the first m points in that array, and return it, which will remove the log n time complexity that we have from add point.
Can you elaborate on? Okay, so I like this thought. Can you write down the time and space for both of these?
Yes, so we the first turn. Yeah, so now let's go through the time of this. So the input is going to be um, obviously just 1 point. But now this is, of course, since we're sorting, this is going to become n log n because we're sorting each time. So if n is however many points we add, the time is going to be n log n, and the space is constant, or not constant, linear. So that's going to be O of n because we have a growing array of exactly size n points. And of course, and sort each time based on their distance to origin, like that. Now in m closest, if all we're doing is just going through the first m elements of this array, then we're just gonna have time is gonna be O of m, and space is also O of m.
That looks good to me. Um, Yeah, we're almost there. We're close to being there. I'm closest. I'm very happy with that.
Okay.
Let's talk about add point. Okay, so
Okay.
so let me write some stuff down. Okay, so follow this train of thought, right? So we're doing add point. Let's
Yeah.
say at any given point in time, I call add point a whole bunch of times. Okay, blah blah blah. Now your list is like this. Okay, your list contains this. So it contains one one, two. You can easy math. Okay,
Sure.
three three, and five five. Right.
Sure.
So this is our list. Okay,
Hmm.
and it's sorted because you sort it every time. Okay. Let's say
Yeah.
now I want to call add point surprise 4 4. Okay.
Hmm.
What time complexity should this take?
Like based on the proposal or based on what
Based on
it
the
should take.
based on you don't so this is not so I'm hinting that the add point we can improve it a bit here, right? So this is your current list per se.
Hmm.
Um, that makes sense. But how would you like to be able to perform add point of 4 4?
I mean, by looking at it constant, but ideally like log n because we can just do a
Mm-hmm.
binary search.
That's right. We should be doing a binary search on this one. But in this
Right.
case, right, let's say for example, we had 1.5, right? 1.5.
Hmm.
And let's say in this case we had, what's a funny thing to talk about? Let's say we had we have endpoints. We have a billion points in here, right? We
Hmm.
have a billion points in here.
Hmm.
What would be the complexity of adding 1.5, 1.5, even if you're doing binary search?
Well, it would be, yeah, log of a billion points, which is
It would still be
unnecessary.
log n, but
Log n. Yeah.
if you're using a list and add a point at index one, sorry, index one, what is the
Hmm.
complexity?
Oh, that'd be linear time
That would
because
be
you have to
linear
shift
time.
everything else down.
That'd be
Yeah.
linear time. Okay, but that's a correct train of thought. We have determined that we want to use binary search, and we do not want to incur a translation policy, a translation, like translating the rest of the array. We don't want
Yeah.
to incur a translation penalty. What structure can we use here?
We can use a hash map.
We can hash maps one option, but it's a bit more complicated. Are there any other sorted? Because this is a sorted list. Are there
Uh-huh.
any other sorted data structures which allow for insertion without having to shift everything around?
Let me think. Again, any other sorted data? Like, yeah, there are. I'm just trying to figure out which one it would be
Start listing them.
in this.
Start listing them, and let's see why you think they're not valid.
So me.
So one idea, right? Let's just let's talk about it, right? So you said hash map. Okay, hash maps aren't sorted, but there's a linked hash map, right? Well, sorry, this is Python. Okay, I'll split it a bit. There's a linked hash map. Wait, sorry. Do you know what linked hash maps are?
I don't.
Okay, never mind. Okay, that's not a hint. Don't worry about that. Hash map. That's one option. Okay. What other structures are there? Go back to your data structures course.
I don't know. Let's see. There's a stack.
There's a stack. Okay.
There,
What
we
else?
can use a queue.
Queue.
We
That's
can
the same thing as a stack.
use
Okay.
the thing that's tripping me up is specifically sorted. That's what I'm
What other structures
we
are
can
there?
use a
Yeah.
we can use a linked list.
A linked list is an option. Linked list is an option.
Linked
But
list is an option.
a linked list is an option, but it wouldn't work by itself. But it is an option. So tell me about what your idea is for linked list.
Well, yeah, so my like memory is a bit fuzzy, but
Okay.
in with a linked list, we could the insert operation could be optimized based on how we implement it. So in the example that you proposed there, 1.5,
Yeah.
1.5, we
Yeah.
could just change, we could just obviously um, change two pointers, and then that's the extent of the work that we have to do, and then everything else can remain as is.
That's true, except how would you know where the left and right pointers of 1.5 are?
Well, yeah, then you'd have to do a binary search to figure out which like
And what's the complexity of
index
binary search with a linked list?
that would be linear.
Correct. So that wouldn't work.
Yeah. No.
But notice something you said pointers. Updating pointers are constant time. What other data structures use pointers?
Data structures use pointers. Um, Now I'm on the spot, so I'm forgetting. Let me think. There's linked lists. There are regular arrays. There's doubly linked lists. Hash maps, stacks, queues, graphs, trees.
Oh, there you go.
Yeah,
Trees, binary trees, a sort of
binary
binary tree.
trees. Yes,
Okay.
yes.
What's the
That's what
what's the,
that's the
what's the
structured
what's
one
the
here.
thought? Yeah, what's the thought process here?
Now the thought process is if we have a binary tree, that will that'll eliminate the issue that we had earlier of the translation cost for just inserting the point.
And can
And
you
the
can you
search
explain that?
time is because we won't need to because whatever the right side or left side of the tree is that we're not looking at, we don't need to change all of those pointers. They can remain as is,
Correct.
right? So
And
then,
so
so
and that's true for updating pointers. Can you now also now justify why the binary search will be log in? Because that was the issue with linked lists, right? Linked list updating pointer is also constant time.
right. So in this case, so let's say we have, of course, 5577. 33 is the child of 22 here, right?
Yeah, this is.
Okay, let's just put this over here. Okay. So yeah, let's say actually we don't need it because we're just doing 1.5, 1.5. So in this case, this would still be log n because we're going to take a look at 5.5. We're going to go to its left child. We're going to take a look at 2.2. It's less. We're going to go to its left child, and then we just look at 1.1. It has no children, so then now this can be 1.1's right child, and that's it. And now we've looked at a logarithmic number of the elements here. Of course, there's 5, but if there were more, then it would just be log n.
And maybe as like a last kind of mini follow up here, for trees, um, the worst case, degenerate case per se of a tree is a linked list, right? In other words, a linked list is a tree.
Mm-hmm.
Do you know of any mechanisms to prevent our tree from degenerating into a linked list? So, for example, if our add point will be called add point 11, add point 22, add point 33, add point 44, the naive implementation would just make that a linked list, right? So, what do you have any thoughts in mind for how you would safeguard against that?
Well, since it's a binary tree, oh yeah, I see what you mean. So you're saying that it's going to become like 1.1 and then right child 2.2 and then so on, and then it's just going to keep going like that.
Well, yeah, like if for a naive implementation, if you're saying just find the thing and put it to the right, that's what you're saying, right?
Right.
So yeah, so that would be the degenerate case, right? So you call that a billion times, and then you call now, right? And then you do like now I want to add something else. So it's going to be a linear time, because it has to go through other children like that, right? So, is there any ideas you have in mind for safeguarding against this degenerate case?
So that would have to do with how we actually create the tree in the first, like how we're adding each point as we go.
Mm-hmm.
So let me think. If it's a regular binary tree, then the right child still has to be bigger. So I'm assuming you're alluding to something a bit more nuanced than that.
Well, I mean, calling add points 1, 1, 2, 2, 3, 3 up to a billion is a valid input, right? There's nothing wrong with that input.
Mm.
But there needs to be something a bit more clever than just find the element and then add it to the right and then call it a day, right? There needs to be some. This is more of an intuition question. This isn't necessarily something you can get on the spot, but this is just a question about asking, you know, this is a case, right, where it becomes a linked list.
Right. Yeah. Yeah. Yeah.
Do you know of any mechanisms perhaps that we can use to prevent this? Because otherwise, this would be the same thing.
Yeah, this would just end up being the same
Yeah.
linked list that we were thinking about earlier. Uh, Off the top of my head, I don't. If it's a binary tree, the way I'm thinking about it, the children still need to follow a specific order on the right and left. So I'm not sure exactly what we could do.
Mm-hmm. Fair enough. Okay. That's not easy. This is more of a question for like if we had more time, we might follow this question a bit more. But for now, I wanted to just end this mock here. pause here for now for today. I'm pretty happy with the progress. Um, let's just start with a bit of how you feel about how this went, and then I'll go into some feedback for you.
Yeah, sure. I felt like it went, especially the first couple follow-ups and the algorithm itself. I felt it was pretty solid. We had a good kind of dialogue going. It felt more like a conversation than a test, so I liked that. Of course, once we got into the later follow-ups, I definitely did
Yeah.
struggle a little bit.
Hmm.
But I'm glad that we went into those because now I have a better intuition for these kind of problems. So yeah, no, I think I'm happy with the progress. I learned a bit, which is what I kind of wanted to get out of it. I thought the
Hmm.
actual original problem went pretty well, and the complexity analysis went
Hmm.
well. But then, of course, down here it was a bit trickier. So definitely had a bit of struggle with that.
Yeah, for sure. I mean, I think you did very well in the base problem. I'm not sure I saw it before, but I think you did very well in that problem. The analysis was good. So let me just go through some of my notes, and then we can talk about the end there.
Mm-hmm.
Yeah. Okay. So today's question was on leetcode. Well, at least the base question is. None of my follow-ups are on leetcode. This is
Mm-hmm.
the k closest points to origin problem.
Mm-hmm.
Okay. So some things that were off the bat that were very strong were good clarification problem statements, so good notes, good test input, just to make sure things are okay. During that process, you found the duplicate case and the tie-breaking case, so that was good to ask right away. That was very good. Um, one thing I want to say is that you were talking about a hash map early on, and obviously didn't end up using one. One thing I have to say is if you're outlining like ideas and approaches at the beginning when you're not sure what the right algorithm is,
Mm-hmm.
and you say some stuff which you don't end up doing, I think it is worth it to be explicit and say, hey, my end algorithm is going to be like this. We actually don't need to use the hash map because of this and this reason.
Okay.
Otherwise, it might cause some confusion for the interviewer when they're wondering, oh, was this person still trying to do that? Did they just forget about it and they're correct by luck or by chance, right?
Mm-hmm.
So just kind of tie up the loose ends there, right? So
Mm-hmm.
that's one thing I have to say. Now in this case, it didn't matter because you got the correct answer anyways. But for
Mm-hmm.
example, if you didn't get the correct answer and you actually did need a hash map to solve it correctly, then that would be a bad luck, right? Because
Yeah.
it seemed like you actually knew what was going on, but you just forgot or something, right? So just
Right.
clean up those loose ends. Okay.
Okay.
Very good point I hear. Very good note I had here, which is that you're checking in frequently with the interviewer to make sure that you're aligned, right? Asking like, oh, do you understand what's going on? Do you have any questions? That's very good. Always make sure you're saying that because it gives the interviewer the most chances to basically ask what's going on. Okay.
Yeah.
So yeah, so I think that was one of the best points here. One thing is one thing I also note is that this is a smaller detail is when you say you don't need a square root, you originally just said because numbers are positive. That is not a sufficient condition, right? When
Yeah.
I
Yeah.
asked you about that, then you said it's monotonic, which is
Yeah.
the sufficient condition, right? So
Right.
small detail there. What you said before was objectively wrong, but I knew you knew what it meant, but I was just testing you that one, right? So just if you're saying stuff like that in passing, just be aware that if the interviewer is, for example, more mathematically inclined, they'll pick up on that. Okay, so just
Yeah.
just know what you're saying.
Mm-hmm.
Okay, you know that, yeah. So you know the Python heaps very well. You know that's a default min heap. You know how to make it a max heap. That was strong. Strong tuition with knowing when to use a min or max heap. So the max heap is a correct implementation for the original one, and then when you want to use a heap for the entire thing for the follow up, then it is correct to use a min heap. So that was correct. That was well done as well. Um, let's see, that was good. Yeah, that's fine. Yeah, you had a small bug on line 30 originally about the distance check. It's fine. Uh, caught that. Yeah, so original problem was just straightforward and that was well done. Did it very quickly. There's no concerns there. Okay, let's spend a bit of time and talk about the follow-ups because obviously this is the meat of the problem, right? Like I saw in a chat earlier was saying that this is a repeat problem. Yes, it's a repeat problem, but the follow-ups are actually the interesting part. Okay, so um, this follow-up is interesting because and this is true for a lot of problems, like not just this one, right? But whenever you're implementing more than one function, right? One thing you need to think about is that there's a trade-off. There can be a trade-off between time and space complexities of the two functions, right?
Yeah.
So your first your naive proposal was good, and by the way, you always had the correct time and space analysis, so that was also very strong. By the way, that was good, right?
Mm-hmm.
One thing you should ask as a just initial opener is just to ask like, hey, which function will be called more? Which one should we optimize the time and space for, right?
Mm-hmm.
Because that will oftentimes um, inform a process, right? So
Yeah.
just be aware that that is a valid question. You should be asking that sooner than later. Okay.
Yeah.
So that's fine. So your original analysis was still correct, and then the intuition here. So this is the difficult part, right? So this is the part where we're trying to form a bit of we're conversing a bit, right? This is pretty common, by the way, for follow-ups. Like once the interviewer knows like, oh, okay, this person clearly understands what the hell's going on here. We can now talk about some more advanced things. Then the interviewer, you'll notice that it'll become more and more of a conversation,
Yeah.
especially if the interviewer is trying to get more theoretical knowledge out of you, right? So you notice that we didn't implement anything at the end there, and we actually ran out a bit of time at the end. Um,
Yeah.
and that's because I already got the signal that you know how to code. I don't need to see you code anymore. I want to just see you think, right?
Hmm.
And one thing which I had to say here is, whenever you're prompted relatively explicitly about what structures can we use, and you can't think of it, this is what which you can prepare ahead of time. Is just
Yeah.
have in your mind a list of every single data structure, just every single
Hmm.
one, and you should do that by just writing them all down onto a page and look at it once a day when you're preparing for interviews. That way, there's
Hmm.
no way you can miss. Like that. That way, there's no way you can miss it, right? Because like
Yeah.
I'll be a bit honest, okay? When you didn't think of trees after I started listing out like 5 structures, that became a bit of a not a great look. Okay,
Hmm.
right? So, and the reason why I'd say that is because this is one of the first structures that are kind of taught, and especially because the hints I gave before then were, it is node based and it can be sorted,
Right. Yeah.
right?
Yeah.
There's like 3 structures that are like that. Okay, so that is something which you have to review. And I don't know what's up with the other structures. You might be more familiar with those, but trees here were a bit of a weak point, right? Another bit of a weak point here is at the end there. I'll give you. So I'll just tell you, the intended solution for balancing trees. So these are called balanced trees, right? Balanced
Hmm.
trees have a guarantee, have what's called a sublogarithmic guarantee for the difference in height of any subbranch. That's what
Hmm.
guarantees that any node is proportional to log in terms of height.
Hmm.
And this is a thing which is in Python, so you might be a bit newer to program. I don't know if you've done too much programming with Python or whatnot, but Python does not have a balanced tree on in the standard library. Okay,
Hmm.
so that might be why you never encountered it. So the typical solution for these, we would in computer science we use what are called red black trees or AVL trees. These are 2 types of trees which are balanced. Okay, so that would have been the intended solution for this follow up here, is to use a balanced binary search tree.
Okay.
So go study up on that by yourself. Go figure out what that means in Python. Go right. And by the way, I'm not saying don't use Python, but what I am going to say right here is that almost every other language has one. So in Java, all non-hash structures in trees are red black trees. I think C++, the order structures are also all red black, right? I don't think Python has a tree.
Hmm.
So there's nothing to talk about. So just so you know, this is probably a consequence and not of your failure to understand anything, but just because you just aren't experienced with that because you use Python. So just go touch
Yeah.
up on that by yourself, and then you'll be fine.
Okay. Sounds good.
Great. Okay. Anything on your side before I end this?
No, that basically covered everything. So yeah, no, I'm glad that I like learned something new that's more useful than just like ripping through a problem and like that's it. So I'm happy.
Great. Okay. Well, it's great having you on, Anish. I'll catch you later.
Yeah, thanks for having me, and yeah, good luck with the next one.
Bye bye.